Grady Booch returns for, we think it's the 6th, maybe even the 7th time that he has been here to talk about an ongoing project called Computing the Human Experience. It's a large-scale, long-term project. It is going to result in a book that is being published by O'Reilly Publishing, and we hope it will eventually result in a documentary series that we want to try to develop together. You will know Grady as a trustee of the Computer History Museum. His much more serious work, though, however, is involved with being an IBM Fellow who is now working in some of the most important areas of cognitive computing at IBM, which is, of course, the major undertaking at IBM these days. He has recently done a TED Talk, TEDx IBM, that has now been viewed something like almost 700,000 times, I think, on Facebook. On YouTube. So he is becoming a global media personality in his own right, as well as one of our very favorite people. So he's here today to continue the lecture series. Please join me in welcoming Grady Booch.
Thank you.
Welcome back.
Thank you. So thanks for the plug about our documentary work. I am given solace in the fact that it took Carl Sagan about 15 years from the time he conceived of Cosmos till it reached the air, and we're about 6 years into that process, so we have time here. If you'd like to track what we're doing, here's our website, and as I often remind people, every time I gain a new Twitter follower, an angel gets its wings, so please come join us. Ding, I hear it again. For a writer, a blank piece of paper. For an artist, a blank canvas are perhaps both simultaneously thrilling and frightening. It is thrilling because you're faced with your raw, naked imagination, with the opportunity to do anything you might imagine, but at the same time it is frightening because it's like, oh my gosh, what do I do next? Da Vinci once pointed out that a way to begin is actually by taking your canvas and painting it all black, because remember that painting is a matter of bringing things to light out of the darkness. Thoreau, in his later years, observed that the world is our canvas, a canvas to our imagination. You remember where he is historically, because this was post-Civil War. We had seen the fruits of the Industrial Revolution come to play to make transformations to everyone's life. So he was living in a very exhilarating time where there was indeed much promise. And if you consider, therefore, that time of the Industrial Revolution, I think in the book Sapiens, it's well described that this was a revolution in energy conversion. And we saw the move from moving just human labor, horse labor, to steam power, which transformed everything. Computing has done a similar thing for us. And the way I'd position it is to say that computing is a revolution in converting imagination to action. We are in many ways given a blank page, a blank canvas, and we have been given, and we ourselves have created the most exquisite paints, the most exquisite pencils, the most exquisite tools from which we can take our imagination. The question, however, is how do we take that pure dream and turn it into reality? And as a software engineer, that means for me executable code. What is the journey between those two? The general view of the public is that you put people into a dark room in front of machines like this, feed them Jolt and pizza and go away, and they do amazing things. This is how I'd explain it to many, but on the one hand, it sounds incredibly dull, and yet I know from the inside, it's the most fun I've ever had with my clothes on. It really is. It's great. It's fun, it's dramatic, it's creative, and such opportunities to take that imagination and turn it into reality. The journey I want to take you on here in this hour is what stands between our imagination and turning it into code. And as it turns out, there's a spectrum, a gauntlet that we must walk through Think of these from the negative perspective as these are barriers we must pass through. But I prefer to spin it in a positive way to say these are the lines, these are the edges against which I put my innovation. For a writer or an artist, if I have just a blank piece of paper, I've got to use just my imagination. But if all of a sudden I say, let's constrain it a little, let's use just oil paints, or let's just use watercolors, or let's use these subjects, all of a sudden that becomes a catalyst to my imagination. So view these steps in that spectrum not as things that prevent me from doing what I want to do, but rather as opportunities to do the best I can do. Let's start with the really interesting wicked ones. Morality, our own understanding of what's right and wrong. Ethics, how we codify it. And culture, which is a corporate reflection of that. And we'll begin with Hal. You may remember the story in 2001: A Space Odyssey. Hal was a central character, the HAL 9000. And a major plot point hinged around two important events. The first is when Hal was detecting the potential failure of a particular device. And then, in reaction to what the humans were doing, he killed the humans. Now, in our current political climate, you would call this not a bug, but it's an alternative feature. Ooh. Yeah. But look at it from the eyes of Hal, because what Hal did from his point of view was actually perfectly ethical, because he had been given the instructions that this mission was so important to humankind, it must proceed. And he viewed the humans on board as simply in the way. So I'm not saying Hal did the right thing, because from a human perspective, there was tremendous cost. But that story brings into our consciousness the notion that in AI, we're beginning to deal with some ethical problems which hit the ground for us now. Hal is a manifestation of the trolley problem writ large. And if you may think, oh, it's just far out there, it's really a clear and present thing. Of course, today we have the technology to build drones that can, without human intervention, track, follow, and kill an individual. So we know in technology, especially in computing, that some things are possible, but they are not necessarily desirable. So is this a good thing or a bad thing? I think it's a good thing in the sense that it forces us to bring our humanity to bear with what we are doing in computing. I'm a signatory to the Institute for Future Life and their condemnation of using autonomous drones for killing. I think it's profoundly a bad thing, and I will do everything in my effort to push back against it. And I think we must, because we rob ourselves of our humanity along the way. But this therefore forces me to consider, what can I do as a technologist, knowing that these things are possible, to prevent them from becoming manifest? Well, we also see this real in the Muslim registry. And I and others have publicly come out saying, we know this is possible. In fact, we have registries of all sorts of things that are already shaped by our ethics and our cultures and our morality. We have a database for car registration. We don't have a database in the United States for gun registration. Certainly possible. The culture says no. Should we have a Muslim registry? Technically possible. Many of us say, no, we should not. And so this kind of moral issue actually is a call of action to us. And I think we as technologists should not idly stand by, but we should be a voice in the midst of it. As you can see, I'm dealing with a number of elephants in the room, and I can't not talk about this one as well. Uber and their work on Grayball. And I will say this publicly, I've done so already. I felt the developers who actually wrote the code for this, it disappoints me deeply. I'm a member of the IEEE and the ACM, fellows of both organizations, and there's a code of ethics that we have. And one of those bits of ethics say basically, we're going to do things that are within the law for the benefit of humankind. Here we have an example of some intentionality that was intentionally going against the law. Is this right? Is it not? We know technologies say it's possible, but here again is a case where we as technologists must stand up. As I often say, Every line of code we write has a moral and an ethical implication. Some of the things are not as obvious, but here we have an example of that. And so my call to action for any of you is to say, you're going to be increasingly faced by these circumstances in which you can be intentional, and you need to choose what is right and what lives within your integrity of your being. More and more so, computing brings us to that point. Now, these are the intentional things, but there are some unintentional consequences for which we must deal. On the one hand, we see the rise of computing that allows us to have police officers that have cameras on them at all times. Privacy experts will say, you know, this is a bad thing. There are others who will say, but wait a minute, this gives us some degree of accountability. An unintended consequence of the pervasive use of this says also now, if we combine this with facial identification, all of a sudden, we're now doing facial identification of everybody out in public. Not necessarily a consequence that we expected. So again, a circumstance where our technology brings us to bear with social issues, and we as technologists should not remain silent. If you look at any of the sciences, you'll see that we are moving into a realm of computational X, Y, and Z, computational physics, computational chemistry, computational biochemistry. We're building, indeed, artificial life thanks to computation. CRISPR is a good example of this. What's happening in our ability to manipulate genes simply would not have happened were it not for the advances we have seen in computing. So we see another example where we must bring to bear all that we know as technologists, but also all that we bear as humans in the same space. Now, not to leave you with a bit of a downer here, let me look at an unexpected consequence that is really quite exciting. This is not a real human. This is Nadia from a company called Soul Machines out of New Zealand. This group pioneered some of the special effects in James Cameron's Avatar, and they've since produced a company called Soul Machines that has built these human realistic avatars like this. Quite remarkable, because they built a model of the musculature of the human face, neural networks behind it that can learn by watching videos of humans, and it becomes hyper-realistic. One of the things that's happened, which they didn't expect, is that it is such a good realization that those who are hearing impaired can read the lips of these avatars. That's pretty freaking cool. And so here we have the opportunity to build technology that impacts human lives, and what a great opportunity that is for us. So that's the first spectrum we must get through: ethical, moral, cultural issues. The next is that of economics, because like it or not, even though we're dealing with pure imagination, the stuff we do costs money. One clear and present example is what's happening in the area of rare earth metals, that there are increasingly fewer and fewer places we find these things, metals such as molybdenum, tungsten, lithium, tantalum, all these kinds of things that we need for many of the devices we produce. And so all of a sudden what's happening is that we are seeing economic forces that we have scarcity in some places. It's leading to, in some ways, global conflict, because now we find places such as China, Afghanistan, parts of the US that have these as resources. We're going to see competition not unlike what we have seen with production of oil as well. Again, computing drives us to these global social implications. And that's kind of out there, but let's talk about a very real story. And of course, Charles Babbage himself faced this. We're always looking for money, and Babbage himself faced this in the analytic engine. Now, he had some other issues in the sense that the analytic engine probably wasn't manufacturable based upon contemporary technology in his time, but still, he was always seeking money to do what he was doing. Would it have changed history? Probably not, because he was so far ahead of his time. But let me point you to a place where it might have changed history. Konrad Zuse and the Z3. Here we have a brilliant computer scientist laboring away in Germany during the time of World War II. And his Z3 was way ahead of its time. It truly was perhaps the first true stored program computer. But it was electromechanical in its nature. He went to the German government, who, as you might imagine, was a little busy at the time. and said, I'd like some money so that I could take this and make them electronic switches. But the funding was denied. They said, this is not war important. But of course, we know that it was war important for the Allies. We see what happens in the stories of Colossus and all the work that happened around the ENIAC and the like. Perhaps the first example where a particular economic decision really did influence the potential outcome of the war. Imagine if he had been as well funded as Colossus had been. Well, one place we did do a lot of funding was the SAGE. About $10 billion in its time, if you calculate that in contemporary money, that's about $67 billion, which, how many trips to Mar-a-Lago is that? Somebody pull out a calculator. But it's about 3 times what we spent on the Manhattan Project. Nonetheless, what you see here is an effort by a government to say, this technology is so important, we are going to put a major piece of our assets into it. Now, the curious thing about the SAGE, and go visit it, there's pieces of the machines downstairs, which is just wickedly cool to see. Look for the ashtray if you haven't seen it yet. I don't have an ashtray on this one. For some reason, Apple left that one out. The curious thing about the SAGE is it was never used in anger. We used it for mistake a few times, but in some ways it was kind of like what Reagan did in Star Wars, meaning we never hoped we would deploy it, and yet its mere presence forced our competition, in this case the Russians, and well, actually in both cases, to give pause, to say, wait a minute, maybe we shouldn't go after the US in this way. And obviously there are many, many other consequences of what happened in SAGE. But here's one example where a concentrated economic effort really made a difference. In our current world, we see a little bit of a different economics, and one of those bits is that we have the economics of increasing returns based upon the fact we have literally billions upon billions of common users. No one individual could say, I want to build an internet pipeline between 2 countries. But the economic forces of capitalism, the economic forces among countries have led to the wiring of our world from which every one of us has benefited. Now, that very revolution also led to a fascinating change that was really at the cusp of where we moved from mainframes to personal computers and where we are today. And that's the switchover where all of a sudden the cost of a machine became less than the cost of the human to program it. And in our microprocessor era, that was where the switchover happened. And so all of a sudden, the economics of development changed radically. Back before that time, when machines, the giants walked the earth, and machines were indeed very, very expensive, you would have lots of humans that would sort of feed those machines. Today, they're very, very personal to the point we put them inside our bodies. And that economic shift, which happened for many forces, changed everything. Now, one of those changes, which leads us to the next step in this, is how we organize our resources to actually build these things. The common view the public looks at computing is to say, you have some really smart people and you give them what they need to do and magical things happen. This is sort of, kind of true when it comes to small systems, but when you want to have something that has an economic impact upon many individuals, it requires more than just one. You may have the image from the Social Network movie, Aaron Sorkin's movie, where you see the programmers from Facebook sitting around a table, sort of trying to one-up themselves in a particular algorithm. That's a common image, but that's not reality if you're on the inside. And a good way to consider it is consider how the pyramids were built. This was not built by one really strong dude, but at least as far as we know, unless you take the alien conspiracy theory, but let's not go there. But rather, it required a division of resources. And not a lot written about it. There was some emphasis that maybe it was all slaves that they brought into it. Current research suggests that maybe it wasn't so much slaves, but it really was an important part of the economy, an infrastructure activity, if you will, that led to the division of resources, the specialization of skills, and the orchestration of tens of thousands of people to make this happen. Now, plant that image in your mind and look here from World War II. And we see some remarkable parallels. In the grand sweep of the history of computing, and this is sort of how I'd explain it to a middle school person, there were a few common phases. We were first computing numerical things. So we were off taking mathematical equations. We learned how to automate them. Then all of a sudden we determined that we could do symbolic things. Those numbers could have meaning. They could represent people or places or things. And that led to another generation of it. But then all of a sudden we moved to computing that was truly simulations. We started building our own worlds. We started simulating physical systems. We started simulating businesses. We started simulating ourselves. Now we're in the cognitive era. We're building systems that are very much human-like, inspired by we as humans that can reason and learn. This came from an era in which we were designing systems that were still largely numerical in order. And in fact, we see here a number of computers. Of course, as you know, women were the computers back then. Computers were human, as the book says. And the way we would organize them was generally through these kind of pipelines. You take one bit of calculation, divide it up among these set of women. The output here would go on to another set, and so on. Richard Feynman was in charge of a variety of computers in the Manhattan Project, and this is what went on. A curious thing happened when you saw things like the ENIAC come into play, because now programming actually became a thing unto itself. We didn't call it programming then, but literally what would happen is that a handful of women, and it was mostly the women, were generally given these mathematical equations and desired outcomes from the men mathematicians and said, go program these, go design the plug boards so it does the right thing. I view this as the beginning of agile programming, to use it in our current phrases, where you have a small team very focused upon incremental outcomes, and they're building things that work each time. So we began to see a split in the programming world in which it wasn't just taking these masses of people, we could automate the process, but no, there was a tremendous amount of creativity associated with it. Look today, this is a war room from Spotify when they launched Spotify globally. And you'll see the stuff that's going on here. Very different space. First off, it's highly automated. They're using the machines themselves to deal with the release itself. And there is a bit of separation of concerns among the various folks. Those who are worried about the network, those who are worried about storage, those who are worried about connectivity, those who are worried about the actual UI itself, all coming together. Now, again, in the history of computing, you can also define a couple of different phases in which the way we built software. In the earliest days, it was, give me a general problem, leave me alone for a while, I'll figure it out. But then it became a little bit more formal, again around the time of Sage, when the stakes for programming were much higher. The economic costs were so high that the cost of error was something that we needed to invest in up front to prevent that error. And that's what was born, what we call the waterfall approach to software development. And in its time, it made a whole lot of sense. Because we knew how to build battleships, we knew how to build tanks, we knew how to make 5 billion screws. Why not apply those same ideas to software? So we'll carefully design our requirements. We'll design a solution. We'll go off and build it. We'll go test it, and then we'll maintain it. And that made a lot of sense, especially given the economics where the machinery was more expensive than the humans themselves. But as software became more complex, as our computers became much more adept, we found that this model simply didn't work, because now all of a sudden the cost of change was so enormous toward the end, and yet our ability to deal with it up front was now so less, we could have a different model. Wynne Royce was the gentleman who first codified this idea, if you want to get some names in history, and in a wonderful twist of fate, his son, Walker Royce, tended to work on the revision of it, which is more a spiral kind of model. Think of it as the rebellion of the son against the father, if you will. And this is the idea that came from Barry Bain, which said, let's design a little, let's code a little, let's test a little, let's learn from it and move on. And again, the economics of computing made this possible because the cost of building things was so much less than it was before. And this is really the roots of what we call agile programming. So if you look at a traditional programmer today, this is pretty much what we're doing, but there is an historical basis to it. Well, we've gone through a transformation. Now that's one way of looking at it, this process. And the cool thing about this process is that it gives us, in each step along the way, great opportunity to innovate. Another way to look at it is, how do we organize our people? The architecture of our systems, for me, is just as interesting as the architecture of the people who build them. There's a colleague of mine, Jim Copleen, who has studied the organizational architecture of teams. And I think this is a fascinating study into itself. If you are looking for a PhD thesis, this would be a good one. How did teams organize themselves then, and how do they do so now? This is kind of how it looks today. That you see in the center of many projects, project managers and architects who tend to work very, very close together, this binary star, if you will, and then orbiting around them a set of developers and testers and requirements folks, and also very close to them, customers as well too. This is the real nature of how we tend to build software today, and it's not how it was a couple of decades ago. The great thing about this is it gives us a speed of development that we simply could not have witnessed before, and that's exciting and frightening at the same time. Another element where organization comes together with economics is in the fact that this very model has led to the economics of outsourcing, which also has had unexpected consequences. So we see often the creation of wonderful ideas here, but the reality is, to take a great idea, one person might come up with it, but it takes hundreds, thousands of people to actually make that manifest and put it in the world. It's more than just writing some great code and saying the world will be a path to your doorstep. It requires a team of people, if you will. It takes a village, if you will. And so in that sense, we see the economics are such that there are some elements of what we have learned in building software that become commodities. Commodities that now can be dealt with on the open market. And as you might imagine, this has led to all sorts of interesting consequences. Not just the outsourcing, but what we see happening with the H-1B visas as well too, is a result of the economical change in software development itself. Now, let's move to the next phase in this spectrum. The things I've talked about thus far are largely human in nature, social, human, collaborative in nature. And now all of a sudden we're moving to another element that becomes much more technical in its sense, and that's its notion of architecture. Watson is a great example of a significant moment in AI, but it also turns out to be a significant moment in architecture. Here's the backstory that's often not told. David Ferrucci, who was the real architect behind all of this, was working on the East Coast of the US in our Yorktown labs, and he and a variety of people had built some incredible NLP and NLC algorithms, natural language processing, natural language classification. On the West Coast, similar things had been done, and what they were discovering is that we couldn't figure out how to work together. So there literally was a meeting between an East Coast representative and a West Coast representative, I think here in Silicon Valley, where they said, what can we do so that we can take the best of our algorithms and make them work together? And from that meeting, they created a thing called UEMA. Don't worry about what it means, but it's a pipeline. So the way Watson works, if you get under its skin, is to say, I take a question, I use a variety of AI algorithms, classic stuff, and I sort of parse that thing. And now all of a sudden I take that parsed thing and I go look out in my body of evidence and I find 10,000 possibilities of what it might mean. And so we see from a simple statement to 10,000 possibilities. That goes to the next step in the pipeline, where I take those 10,000 and I now look for evidence to support it. And those 10,000 might grow up to 100,000 or a million possibilities. That's the next step in the pipeline, forward chaining, backward chaining. And then having done that, I rank them. So I do some statistical techniques where I then say, based upon these million things, what looks the most promising? And I'll rank them after having retrieved them, and the result comes out. The trick was to do that in a few milliseconds. And so the architecture was really the breakthrough that made Watson happen, that brought together all of these really cool things together in one place and make them work. In fact, I have to be very clear, even though I'm working with Watson these days, I am not a cognitive scientist. I'm a systems engineer, because I'm viewing the world and opportunity as being, let's take these AI things and engineer them as a system, as opposed to viewing the world as an AI problem that needs to be engineered. And the result of that point of view, it yields things like Watson and what we can do beyond. Now, this notion of architecture is an interesting one because it actually has deep roots in other worlds. There is, if you look in architecture, in civil architecture, you'll find that there's a whole body of work around various architectural styles. And what you'll learn from that is that those architectural styles represent things that have grown up over the years. Somebody tried something, it worked well, and the forces of that space led us to build upon it incrementally. The very same thing happens in computing. A great example of that is Doug Engelbart and his Mother of All Demos, in which it's a brilliant video to watch, in which he presented things that we take for granted now. But consider what he did in his time. He, pretty much alone with his team, architected a solution that gave us behavior that was utterly transformative. As Vint Cerf says then, what happened is that Doug Engelbart built basically a one-host web. But then it took Tim Berners-Lee and Mark Andreessen to make it work for billions, millions if not billions of people. A common story in the history of computing, a common story in the history of civil architecture, we find one brilliant idea, hardened by technology, hardened by use, all of a sudden, thanks to the organization, which we talked about before, makes it possible for us to make this manifest in the real world. Zuckerberg did the same thing, in which he, pretty much alone, handful of people around him, as he added on, built the Facebook. I've desperately been trying to get the original source code that Mark wrote. It's out there someplace. We haven't been able to dislodge it. And that's why I'm so excited by the museum's activities of being intentional about gathering source code, because it is from these things that the larger architectures come to be. Go look at Mac Paint, which is publicly available on the museum site. And if you study it, I agree with what many have said, that it is perhaps the most beautiful piece of software I've seen. It's great. Now, my wife may disagree with me, but I find beauty in software. I look at it and it just, takes my breath away. I'm sure it does some of you too, but you know, we're geeks, and that's okay. But the point is, you see the roots of these wonderful ideas that then become transformative, and that's what's happened in Facebook. But that being said, let me say that the world is not exactly like what Mr. Robot or Westworld deals with, because there's a little thing there that nobody ever talks about that, and that's legacy. For me, software development is an interesting thing if nobody's ever done it before. I'm starting with a complete blank page. I can have complete innovation, but the reality is that for many systems that matter, we often end up with millions of lines of code that therefore begin to inhibit our creativity. I think, as I mentioned in one of my previous lectures, I had the opportunity to work with the IRS, in good ways, mind you, is good ways. Grady would like to see you. Oh. Okay, I'm not going to release my tax returns until my audit's finished. That line doesn't seem to work. But I discovered that working with them, they've been trying to go through a transformation of their software for many decades, spent billions of dollars on it, and literally some of the software that still runs today is written in IBM assembly language. Kid you not. So if you have any of those skills, the IRS is looking for a few good men and women who can help them. They'll always have a job there. This is the issue of software legacy. I kind of view software legacy like this, that it's the problem of taking buildings and still living in them and trying to maintain them at the same time. So we think of software development as largely an activity of, oh, this is fun, I start with everything new. In many ways, it's like city planning, because you have these many forces that work around you that make it, that push back against it. Again, moving from an empty page to reality, one of the forces with which I must have to deal. Next up in the spectrum, we have issues of algorithms. Now, alchemists dealt with this in their lifetime. It must have been cool to be an alchemist because you had all this wonderful, stinky, smelly stuff, and you could just try stuff and see what would happen. Problem with the alchemists, of course, is there was no science behind it. Imagine, therefore, if you took the opportunity for experimentation and combined that with deep science, well, you could do some amazing things, and that's what algorithms are all about. I would claim that algorithms are to the modern world as fire and wheels were to the old. They give us the foundation upon which we can build all of these amazing things. As an example, I begin with Shaky. Shaky is very important to me in my personal career. I remember the Life magazine article about this, and I looked at it and said, this is what I want to do in my life. And in fact, I remember before the museum was even here, I had the opportunity to go walk the warehouses, and they said, hey, great. I told them the story, and they said, hey, Grady, go open this box over here. And it was a big crate, and I did. I said, oh my God, it was literally Shaky. So go downstairs and visit it. The interesting thing about Shaky is that it pioneered so many things, including work in algorithms. In fact, its path-following algorithm, the A-star algorithm, turned out to be incredibly important. Here's an animation of an example of some of those, a variety of path-finding algorithms. We're drawing a maze. We're going from the blue dot to the red dot. And here we're using a variety of algorithms that try to calculate a path from here to there. This happens to be breadth first, where I say, let's look at all possible ways, really wide. Then there's a depth first, let's go deep until we have to backtrack. And then there's the A-star algorithm, which was pioneered by the work in Shaky, which is really pretty fast. And as it turns out, A-star is pretty much the foundation of all the map routing algorithms you'll see today. Notice in historic terms how it came to be. We had a real problem we had to solve. We needed to apply a variety of ideas to it. From that was born an algorithm, and from that was birthed things that we could use over and over again. Similar thing has happened with a little bit of hairy mathematics with discrete fast Fourier transforms. Now, I don't want to get too technical, but this is the foundation of a lot of the things we do in communications these days. The ability to take very noisy signals in the analog world and convert them to a different domain, potentially the frequency domain from time to frequency. If I'm doing a spectrum analysis, or if I'm trying to pass a noisy signal across a mobile phone, FFTs are in the midst of that. This is the hairy mathematics behind it, and the breakthroughs that happened in the early days of computing led us to the discovery of how we could actually turn that into something computable. So again, consider innovation. Focused upon a particular problem, the edges on my page, the subject of my painting, it led the industry to focus upon a solution that all of a sudden became the foundation of many things. Now, the examples I've given thus far are largely symbolic in nature, and we're seeing similar things happening in connectionist models. There are two really fundamental ways of computing these days: symbolic approaches and connectionist models, which are more neural network based, which lead us to things like AlphaGo. One of the leaders in Go in the human community, witnessing what AlphaGo did, observed that we have not begun to touch the truth of Go. And what he observed is that computing, thanks to DeepMind, has led us to approach the problem in ways we never could have anticipated. Now, we talked about architecture of buildings, we talked about architecture of Watson. Turns out there's a whole set of innovation going on in the architecture of neural nets. In the earliest days of neural networks, they were simple, one-level kinds of things, inputs going through some neurons to some outputs. Then we discovered multiple layers. Then we started studying the brains and realized there were feedback mechanisms that were very, very cool. So notice the interplay then. The things we know outside our world, like how the brain itself works, inform what we're doing here, and vice versa. So this is the delicious dance we have in algorithms in particular, where we get outside of our comfort space in computing and interact with that world. Speaking of neural networks, let's move now to laws of software, because they are also part of this step in the journey. Carl Linnaeus, in his time, pioneered the ideas of taxonomies in species. He began to realize that there were patterns among species. These things kind of looked and smelled and acted alike, and they were very different than the things over here. It led us to creation of taxonomies like this tree of life, from which we can begin to distinguish the ways in which living things are distinct from one another. A veritable zoo of living, if you will. In computing, we have our own zoo. We call it a complexity zoo. And it reflects the difficult kinds of problems we can face. Now, this is interesting in the sense you must realize that there are some things we may dream about that turn out to be impossible for us to do. Impossible in the sense that we can compute them, but the life of the universe is not long enough to ever do so. Now, again, I don't want to get too deep here, but the notion is to say that from a computer science perspective, there are many levels of hard. There's hard, there's damn hard, and there's expletive deleted hard, to put it in that form. So an easy problem would be like searching a string. I give you a website and I want to search for a particular algorithm within it. That's pretty straightforward. Those are technically what we call polynomial time problems. As the data becomes increasing in size, the solution doesn't blow up. We can do it in relatively linear time, if you will, polynomial time associated with the size of the set. On the other hand, there are those that are called the hard problems. These we call non-deterministic polynomial. It's like taking a graph here and a graph here and saying, are these things matchable? As it turns out, if they're small graphs, I can do it pretty easily. But once I start making them larger and larger, the problem kind of blows up. The really hard problems are those like the traveling salesman problem. You may say, oh, but it's just a programmable problem, simple matter of programming. Turns out it's not. If I have a problem that says I've got these places and I want to visit them in a certain order without ever touching them again, if I have a small number of them, I can use brute force approaches. But the real formal solution is, if you will, intractable. There are so many possibilities, even the best algorithm we cannot find. And as it turns out, there are other classes of problems that are truly unsolvable given what we know. Now, where does this work pragmatically? Well, it all deals with encryption. And as Snowden and others have shown us, encryption is important to us. If you're not doing it now, encrypt your communications. It's a good thing. But the way encryption works, and this is of course unto a talk itself, deals upon algorithms associated with prime numbers. In public key encryption, I have a public key, I have a private key, and I don't give you my private key, but I can give you the public one, and we can actually transform information from one to another. That's wickedly cool. Again, an algorithmic case. But the laws of software are currently working in our favor that say it is so hard to factor really large numbers, we're safe for a while. However, bring on the laws of physics, and to put it politely, yeah, we're screwed. Because now all of a sudden we have quantum computing. On the one hand, much like the technologies I mentioned at the beginning, quantum computing gives us a new canvas upon which we can draw. It gives us opportunities to do things we could not do in the past, but there are also some side effects. Because now all of a sudden, I'm no longer computing in this universe, I'm computing in every possible universe simultaneously. And quantum computing gives us the opportunity to do calculations that would be in traditional systems impossible to do. Does that mean that someday I'm going to have a quantum computer inside here? No, but it does say that computing is advanced to the place where the laws of physics, which once pushed back against us in the symbolic world, we now have a new door that's open to us. And quantum computing gives us a way to solve problems which we could not previously have done before. So that's computational power. Another place where the laws of physics come into play is the speed of light. The speed of light. It's not just a good idea, it's the law. And this comes to play if I'm going to, for example, Mars. If I'm in a low orbit mission, like to the moon, I can rely upon mission control on Earth to help me out if things are going along the way. But if I'm going to Mars, depending upon where we are in the Mars orbit and where we are, we're on average, we're about 15, 17 minutes away, round trip. So if some problem comes into play, we're screwed. Thus, the HAL scenario. If I can't rely upon mission control on Earth, I put mission control inside the Orion spacecraft and on the surface of Mars. The laws of physics impede us in computing, but they also give us some opportunity. And so again, here's a case where, quite legitimately, we'd like to build a HAL-like cognitive assistant that goes along with a Mars mission. That's the speed of information. And then there's density. No, it's not yet Halloween, but it looks like one of those little candy corn things. But this comes from our research labs here, where just recently we found a way to put a single bit in the level of an atom. Today, within hard drives, it requires somewhere on the order of 10,000 to 100,000 atoms to store 1 bit. But we see a path that brings us to putting 1 bit per atom. And all of a sudden, that's amazing density. And yet, we still are limited. The laws of physics intrude due to some consequences of rules of energy that say there is an ultimate density to which we can get. We can get lower than this, but still, as Richard Feynman would say, there's plenty of room at the bottom. I have an incredible palette against which we can build. In fact, one of those palettes is that of encoding information on DNA itself. You can think of it as DNA is life's way of passing information across time. It does it in a rather noisy way, but it still does it in a way that's quite remarkable because it's led to you and to you and to me. And that's a pretty efficient system if you think about it. So whereas the laws of physics might look like barriers to us, they create opportunities. Now, the ultimate end of this says what John Archibald Wheeler says. If I take this to its natural conclusion, he observes that it's not unreasonable to imagine that information itself sits at the very core of physics. Now, look what I've done here. From the beginning of the talk, we recognize that computing has caused us to consider what it means to be human. At this end, we realize that computing causes us to consider what does it mean to be real? What other industry, what other science encompasses so much? That's cool. It really is. I must at this point bring in the classic cartoon from Randall Munroe, XKCD. If you think about it, and he's right, computers are just carefully organized sand. That's really all they are. And what I've described to you here, from ethical issues to economic, to organization, to architecture, to algorithms, to the laws of software, to the laws of physics, these are the ways in which we have organized our computers. In every place along the way is an opportunity for innovation. You may view those as brick walls, but they're not. To quote Randy Pausch, if you haven't seen it, you must watch his last lecture at CMU. I'll quote from him, "The brick walls are there for a reason. The brick walls are not there to keep us out. The brick walls are there to give us a chance to show how badly we want something. Because the brick walls are there to stop the people who don't want it badly enough. They're there to stop other people." So my call to action to you is, don't be those other people. Be those who contribute to taking pure imagination and turning into reality that makes a difference. Those barriers, if you will, view them as opportunities to the palette in which we have. I'll close from a line from one of my favorite artists/poets, a gentleman by the name of Brian Andreas. And I think it points to the importance of imagination. In my dream, the angel shrugged and said, "If we fail this time, it will be a failure of imagination." And then she placed the world carefully in my hands. It's in your hands. Let's go forth and do some cool things. Thank you all very much.
That was fun. I love the cartoons, too. That was really good. let's just get right to the questions.
Sure.
Because we have a couple that clearly indicated that the issue that the reference you made to Grayball and Uber is that's not widely shared. So could you just explain that a little bit more?
You bet. So I'm telling you things that are public. So I get all my information from the press. I have the best press. I have the best words. That's where I get it from. So, and I've not talked to people at Uber, and I'm not publicly condemning Uber. I'm just saying that looking at it from the outside, there's some hinky stuff that went on here that bothers me ethically. Grayball apparently was a program that Uber created, literally a program, that would allow you to identify if a rider was in fact law enforcement or some other kind of rider that potentially might discover some of the things that Uber was doing to bypass the local laws. So it was a clear and intentional way to identify law so that they could skirt the law. And it was purely done in software. And it was the program called Grayball. Uber has since it became public, said publicly, we're no longer using Grayball for these purposes. But here's a great example of it is possible to do things, and yet should we? And I view it as an issue of both corporate as well as personal responsibility. On the one hand, it's corporate responsibility, and I'm not condemning any one company, but you have to say, if I am in such a toxic place that encourages such things, is this a good corporation? And similarly, as an individual, I have a personal responsibility to say, I've been given this, should I in fact move forward and do so? In fact, I have a personal story to that end. I was, in my early days in my career, having gone from the Air Force and then started up Rational Software with some of my colleagues, I did a lot of work in the defense business. And I remember one particular project where they said, Grady, help us in the architecture. I looked at it and I said, basically, this is flat outright unconstitutional. I am not going to do it. And so in the report I gave, I said, basically, technically, here it is, but constitutionally, you're hosed. And they fired me. And I was happy they did, because at least I worked within my personal integrity. I lived with what my beliefs were and did the right thing. As it turns out, I was happy to find out the program was canceled, because others found out along as well. But I think the story in this is that there is a level of personal responsibility we all have in this, and I take it seriously.
There's a related question here, which is there are mandatory classes in ethics in medical school and law school and other sorts of pursuits. Should there be something like that in engineering schools, especially in the area of code?
Do you go to a hairdresser?
Get my hair cut, yeah.
Okay, great.
Yeah.
So you may wonder, why the hell did Grady ask me that question? I would imagine the person that cut your hair probably had to go through more licensing than the person that wrote the software that controls the airplane you fly on.
Yeah.
That gives you pause.
Yeah.
So you've raised a whole issue to a degree of what sort of professional oversight should there be in this space?
Yeah.
And the short answer I'll give you is that I think that it is inevitable someday that we're going to see that kind of thing happen, because there are some parts of software development that are so important to civilization that we'd like that degree of confidence. In fact, in Canada, if you call yourself a software engineer, you actually have to be licensed by the Board of by the Board of Engineering. I think the same is true in Texas and a few other states. So the short answer is that yes, I think we do need to be doing those things, but we aren't quite at the point I'm comfortable where we know how to turn that into action. Give you a good example. There is the Partnership for AI, which I forgot all the companies in it: Microsoft, Google, Facebook, Apple, Amazon, IBM, we're all members. And the IBM representative of this is a woman named Francesca Rossi. And she's been doing great things with them. And I very much celebrate the stuff these guys have said. But I said to Francesca, until you turn this into running code, it means nothing to me. So I challenged her to set up a project where she's going to try to do that. How do I actually do, in her case, it's embodied decision making. So I want to take those ideas and make them real. And it's not everybody that has to be able to do that, but I think there's a small and growing class of developers who I would like to be, that intensely understanding of the issues. And those I would like to certify to some degree.
You just gave me a great opportunity to mention that this fall, one of our strands in our live event series is going to be the partnership on AI. And
excellent.
We'll have representatives from every company in individual discussions talking about what this partnership hopes to achieve. Maybe you can come back and represent IBM.
Or Francesca.
Or Francesca. So here's someone who was really taken with what you said about creativity and collaboration and the algorithmic model and intelligence, and take that to Washington, D.C. Is that possible to take that kind of approach to something like policy making in Washington?
Oh my God.
We need some help today.
I'm sorry, John. I'm afraid I can't help you. I'm afraid I can't do that.
It's like Dave,
That's
right?
like Dave. I've been told that there are 4 senators, 4 congressmen with a computer science background who are now in Washington. That's encouraging. Ted Lieu, I guess is his name, from California is one of them. We follow each other on Twitter of all things. The deep part of your question is, let's couch it in the term of computational politics. The one encouraging place I see is that computing can play a role in the increasing transparency of governments. Open data things and like that, I think, are powerful and important because they yield accountability to our governments. I think there is opportunity, although we're a long way away, from having any kind of computational decision making in politics, although I'm hopeful. We've taken the entire body of US tax code and put it inside Watson, and we can begin to reason about it. There are a few startups that have begun to embrace legal code and begin to reason about it. So we're learning ways in which we can build AI assistants that help us understand the ambiguous, self-contradictory code that's out there. And those increasingly, I think, will become tools that community uses. Honestly, I don't know what it's going to take to transform the government. Sometimes, to use a phrase, you have to destroy the village to save it. And in computer science terms, I call it as a matter of refactoring. The government, most governments of the world are in serious need of refactoring, but I don't know how we get there. Last thing I'll mention, I was doing a thing for IEEE 2 days ago, and somebody said, "Grady, you should run for Congress." And I said, "No."
By the way, while you were talking, and you may know this, within the last half hour, Paul Ryan has pulled the health care bill from the floor. So
I'm shocked. Shocked, I tell you. Shocked.
All right, here's one on autonomy, which says, I'd like for my next car to be autonomous. Please expand on we talked about the negative use of Uber's current efforts, but do you think that, are there good and bad potential uses of autonomy in the driving scenario, just the way you mentioned about Uber monitoring its customers?
So let's talk about autonomous cars. Obviously, there's tremendous advantage. On the one hand, as I drive the streets of the Bay Area, it really sucks to be in traffic here. It really does. And so to have some means of reducing the amount of time, or the time I can be productive, that's great. On the other hand, if I were a really evil genius guy, I'd see autonomous cars as the perfect bomb delivery vehicle. Truly is. Ooh, yeah. How do I counter that? And I don't know the answer to that one. I think the net benefit is good. I think the downside is something, it's true of any technology. The last thing I'll say on this is that I'm more of a proponent of, well, I love Elon Musk dearly, but I think he's on a path that I don't necessarily encourage, which is the notion of fully autonomous vehicles. I prefer to view it as human augmented vehicles that do things for me, but I still want to have a steering wheel. Maybe I'm old school. I like books too. I like physical books. I'm just an old fart.
What do you think, now this is the way, I want to read this exactly the way it's worded because the way it's worded is really interesting. What do you think we will see when we are close to the singularity?
I'm parsing in my head because I want to say something that's not libelous. I think the idea of a singularity is profoundly stupid. Not to condemn anybody who supports the idea of singularity, but the notion of there being a moment in time that we transform across, it's not going to happen. I'm very much of the line of Rodney Brooks that says we'll never see a singularity because we ourselves will have become robots along the way. So I'm very much of the notion that we will be in a coevolution for the next several generations. And so it's not going to be a singularity that happens at this moment in time, but rather it's going to happen through that evolution. So that being set aside, let's dance around what I mean by singularity. There will come a time, certainly, where we have devices that are very human-like, that reason and that learn, and that even more so learn how to learn. That's frightening for some. I think it's frightening because it challenges our very humanity and causes us then to consider, are we irrelevant? And one answer to that is to say, well, yes, those kinds of things can actually rid us of the things that make us not human. Look at the child labor that we saw in the early days of the Industrial Revolution, where people were put in the places we now have machines. The same thing is happening as well. There will be human cost because of the transformation, and no doubt that people find meaning in work itself. We've got to deal with that. But on the other hand, I am optimistic because I think these kinds of things will indeed enhance human life as opposed to take away. So to answer your question shortly, in short, I don't fear the singularity. I embrace whatever there might be around it because it gives me an opportunity to be more human.
That's wonderful.
I'm an optimist because to not be an optimist is kind of a downer, right?
It is kind of a downer.
I'd add to that by saying, being a student of history, we've, as a human species, have gone through some really rough times. We, think about all the terrible things in our world, but the reality is that we live in the most peaceful times across society than you ever might have imagined. There are fewer wars that kill as many people. We have the capacity to have enough food for everyone. It's the human things that are preventing us, and that is opportunity, and that's why I'm optimistic.
Speaking of the human things, that leads directly into this question that I have here on the current debate and the discussion about inclusivity, diversity, culture, especially the whole notion that if this increasingly intelligent body of computing is designed from only one perspective, we're going to end up with a body of computing that may just simply replicate rather than widen this whole sphere of inclusivity. Yes. What do you think about that, and what do you see that you're encouraged by in the profession that addresses that?
Well, the problem is real. In fact, if you look at many of the existing systems, they're built by young white guys in the valley. That's the reality of it. And therefore, many of them embrace young white guy morals and ethics. But it's natural. I think what encourages me is the fact that we recognize that's what's happening. And so there is at least an awareness that the machine learning we do does have its own bias, biased in ways that are tremendously subtle. And so the fact we're aware of it encourages me. The fact that there are groups such as the Partnership for AI, OpenAI, the Institute for Future Life that are, raising flags and clanging bells about it, saying it's real, I think that's encouraging. Again, why I'm an optimist, because in the end, our human systems seem to have these checks and balances that do save us in the end.
One final question for the programmers in the audience. Why didn't Ada catch on?
It was ahead of its time. It really was. And of course, my history with Ada, that my early work in software engineering was with that language. Jean Ishbia, the designer of the language, and the others around it, took the best we knew in software engineering and brought it to it. But if you look at modern languages, the idea of generics, exception handling, object inheritance, these kinds of things, they're in our languages. So it was ahead of its time. I think I'll answer the question in short by saying this. It was technically ahead of its time. And second, nobody likes to have things imposed upon them. And that's what the government did in this case. Remember that Bjarne was evolving C with classes about the same time, and there was no such mandate. It found grassroots support in the non-defense world, and it was around the time where more and more non-defense computing was playing a role. So if you had brought something like Ada up today, it would be a very different thing. I could ask the same thing about Smalltalk. Smalltalk, I pine for you. It's still my favorite language.
What's next in the series on computing the human experience? What sort of ideas are percolating?
Thank you for asking. So if any of you have a spare 6-10 million, please come see us.
We'd like to make that documentary series.
That's right. So in terms of the series we're working on, we're turning our attention to doing the book itself. We've now seen 6 or 7 episodes in what we're trying to do here. We did one on what it means to be human, computing in conflict, computational thinking. And now, and again, thank you for the forum, it's given me an opportunity to, you're my guinea pigs, to try out some things. We're at the point we're ready to go find that next producer to make it real. And we have the book contract, as I mentioned, so I'm busy writing as much as I can.
That's
There's
great.
so many stories to be told here. The thing I find as I get deeper into this, I have to not talk about things because there's so much exciting stuff going here.
Thank you for bringing all this to us, not just today, but in the programs we've seen in the past, and we'll see you again soon.
Absolutely.
All
Thank
right,
you so
thank you.
much. Thank you all.